Section 2.1 was about structure functions. This begins section 2.2, which is titled Minimal Path Sets and Minimal Cut Sets. Here's the idea. So far, we have seen two different ways to describe the arrangement of components in a system. The first is the structure function, and we use the Greek letter phi for a structure function, and its arguments are x. So for example, if I have a two-component system, the two arguments will be x1 and x2, and if those two components are arranged in series, then the structure function will be x1 times x2. So that's one way to define the arrangement of components in a system. A second way is to draw what's known as a reliability block diagram. Sometimes these are abbreviated RBD for reliability block diagram. There is the reliability block diagram for a two-component system where the components are arranged in series. So those are two ways to describe a system and how the components are arranged in that system. In this section, there's going to be two new ways to describe the arrangements of components in a system. The first is minimal path sets, and the second is minimal cut sets. So we begin with a definition. The notion of what it means for one vector to be less than another vector is not clear and needs to be defined. So in reliability, the way this less than is defined is it says that every value in the x vector is less than or equal to every value in the y vector. Furthermore, for at least one of the components, xi is strictly less than yi. Now there's going to be definitions of greater than or equal to, less than or equal to, and those definitions are analogous. Now one bonus that comes from defining these things called minimal path sets and minimal cut sets is any coherent systems of components can be written as a series arrangement of parallel subsystems or as a parallel arrangement of series subsystems. So here is the definition of something known as a path vector. A system state vector x is a path vector for a coherent system if phi of x is equal to 1. So if you think of this set right here as all of the 2 to the n system state vectors, then there is a subset of those system state vectors which are going to be called path vectors. So here are the path vectors, and they correspond to an operating system. A little bit later, there's going to be something defined called a cut vector, and a cut vector is associated with a failed system. So every possible state vector has to either be a path vector or a cut vector. Two other names for path vectors which you might see out in the literature, they can be called link vectors. They can also be called tie vectors. So here is a second definition. A path vector x is a minimal path vector. So some of these path vectors are special in they are called minimal path vectors for a coherent system if and only if phi of y equals 0 for all y less than x. So intuition 1 here is that a minimal path vector is a path vector for which the failure of any functioning component results in system failure. You'll have to go back to the definition of less than for vectors to see that that's a reasonable way to interpret these. So some of these path vectors are special, and I'll break them out this way, and they are known as minimal path vectors. The second intuition associated with these minimal path vectors is they are on the edge in terms of they are a system that if any component fails, then the system is failed. So these are vectors that are in a perilous state. They are right near the edge in that any one operating component that fails means the system fails. A little bit later, we're going to see within these cut vectors, there's also a special group of them called minimal cut vectors. And these minimal cut vectors are failed systems, but if you repair any of the failed components, then the system will be operating. So they're on the edge in another sense. And that Venn diagram, I think, is a helpful way of thinking about path vectors, minimal path vectors, cut vectors, and minimal cut vectors. Okay, here's an example. Let's find the path vectors and the minimal path vectors for this system. Now, since you have 3 components, you know that there are 2 cubed, or 8, system state vectors. So you know that that's the case. And of those 8 possible system state vectors, these 3 right here correspond to an operating system, which means the other 5 system state vectors correspond to a failed system. The minimal path vectors in this case are 1, 1, 0, and 1, 0, 1. Let's take a look at this one right here. What does 1, 1, 0 mean? That means this component is operating, this component is operating, and this component has failed. That particular system state is right on the edge, isn't it? Because if components 1 or 2 fail, then the system comes down. So those are min path vectors. And the other vector, which is a path vector, which is 1, 1, 1, what does that correspond to? Component 1 is operating, component 2 is operating, and component 3 is operating. That does not satisfy the definition of a minimal path vector because component 2, for example, could fail and the system is still operating. And that's one of the 2 vectors y less than x, such that phi of y is still 1. So now we have our path vectors, these 3, and we have our minimal path vectors, which are these 2. And here's a new definition. The set capital P, which is the set of all indices I, such that xi equals 1, is a minimal path set which corresponds to functioning components in the associated minimal path vector. This is italicized because it will have a different meaning for cut vectors when we get to them. So here is the idea. In this first minimal path vector, 1, 1, 0, the indices associated with the operating components are 1 and 2. In this minimal path vector, 1, 0, 1, the operating components are in sets, or are in components 1 and 3, so that is our second minimal path sets. So as I look at this system, I could draw a line through 1, 2, and that is the first minimal path set. And then I could draw another line through 1 and 3, and that becomes the second minimal path set. In general, for a set of n components, we're going to denote the min path sets by P1, P2, up to P sub s.